Hello everybody, my name's Stephen Barrass. I'm from the Faculty of Arts and Design at the University of Canberra, and today I'm here to admit that I'm a self-quantifier. That's right folks, I believe in self-improvement through numbers, and I'm here to tell you all about it. This is my blood pressure monitor on my wrist, and here you can see my blood pressure monitor app on my tablet. It shows my regular measurements of diastolic and systolic blood pressure, which are the low and the high pressure in your veins as your heart beats. As it turns out, 1 in 7 Australians has got high blood pressure, and although there are no obvious symptoms, many people don't actually realise that they have high blood pressure. And for this reason, it's called the silent killer. And that's because over time, high blood pressure in the veins causes all sorts of chronic diseases such as heart attacks, strokes, and organ failure. So it's not a very good thing to have, and it's something that you want to keep track of and do something about. Medical experts advise that you should have your blood pressure tested regularly. Well, on to self-quantification. I became a self-quantifier because I started measuring my blood pressure on a regular basis to keep track of it. And this meant that I started looking at the charts of the blood pressure, and to tell you the truth, they were a bit boring and they weren't very inspiring. I mean, when it went high, okay, it did stress you out. It tended to make your blood pressure go up when you saw it high. Sometimes it was better not to look. And I started thinking about what other ways could you use to explore this data and experience this data and think about the data? Could there be a better way to engage with that data set? So previously I'd been exploring the idea of acoustic sonification in some experiments at ICAD in 2011, where I presented some bells that I'd 3D printed. Here's one. They're called HRTF bells, and there's a paper about those that's that's referred to in my paper. Anyway, it's a data set that modifies the shape of a bell, and the bell rings. And this led me to start thinking about other kinds of acoustic objects that I might be able to use to represent my blood pressure data. And in thinking about that, I started to explore the 3D printing of musical instruments, and I found that there was a fairly active and developing community who are interested in 3D printing musical instruments. Here I've got a whistle, 3D printed plastic whistle that was uploaded to thingiverse.com in 2009. Caused quite a lot of interest because it was one of the first, maybe the first object that had been 3D printed that could also make sounds. So I 3D printed it. Unfortunately, it doesn't make a sound. And that really highlighted to me the fact that there is really an intimate coupling between shape, material, and sound. And I found some further experiments from Arvid Jentz, who did a master's on 3D printing of musical instruments. And he did 40 experiments, which he documented, and found that the sharpness of edges, the kind of material. There are many factors that influence the acoustics of 3D printed musical instruments, and most of his experiments didn't work. Well, I thought about all the kinds of instruments that Arvid had tried, and tried to think of a metaphor that would be really good for blood pressure data. And the one that, I don't know, somehow came to mind was the idea that blood pressure is often linked with anxiety or stress, and that meditation is often seen as an alternative medicine, an alternative therapy for anxiety and stress. And the additive link there was that meditation is often linked with singing bowls. So here is a singing bowl from the markets. It's a mass-produced singing bowl, and as you know, when you rub the edge with the puja, it starts to sing due to acoustic resonance effects. The shape of the bell starts to vibrate in various different modes, three-dimensional modes, some modes around. It's partly due to the circumference and the depth and the thickness of the bell and other acoustic factors. So I thought, what if I take that approach I used with the bell and try it with a singing bowl? So I collected, after a year of uploading I had a year's worth of uploaded blood pressure data, and I decided to map it onto a bowl instead of a bell, which is pretty much the same as a bell without the handle. And here is my first effort to do that. It's actually really thick because there's limitations in 3D printing of metals on the thickness of the walls. So I sort of had to make sure the walls were thick enough to print. And it's really heavy, and but what you can see is the variation in the profile there. The mapping I chose, which is fairly arbitrary, was just to map the data. This is systolic pressure on the outside, and on the inside, if you have a look in there, the thickness of the inner wall is modulated by the diastolic data. So they are kind of fairly irregular. It's really much like the graph. It's kind of really pretty much mimics the graph from the iPad as a way of modifying the wall thickness, which is similar to the approach I used on the bells, which is all well and good, and it printed, and actually it rings just like a bell, but doesn't actually sing. Bit of a shame, really. Doesn't matter how much I do this, it ends up not ringing. Back to the drawing board, I thought. And when you look at it, the real difference between that, besides the slightly irregular shape, is the thickness. Look how thick that is. This one's only 2 mils thick. This one's like 5 mils thick. And I guess this is just too thick to actually flex. It's so rigid that it actually doesn't build up the travelling wave or the resonating, the resonant flexing that's required. So I was back to the drawing board. So one of the things I could have done was redo the shape mapping to make the walls thinner, but that didn't really work because I couldn't guarantee a minimum thickness that could actually be 3D printed. So then I started thinking about other approaches. How else could I map that data to the bowl? And I came up with, here's a plastic prototype that I used in the next round just to save the expense, because printing in that much metal is very expensive. And actually there was a mistake in this 3D model, so the bottom's actually... So it was a very good idea to do some prototypes in cheap plastic before you go to metal. But of course you still don't know whether they'll ring. But in this prototype, what I did was create these spokes, which vary in thickness. The bottom thickness is the diastolic pressure and the upper thickness is the systolic. You can see I've got a year's worth kind of rotated, mapped around. So instead of varying the thickness now on the inside and outside from the bottom to the top. I've actually varied. So before the days over the year went from the bottom to the top. This time the days for the year go around. So you can see there's lots of different ways you could map the data onto the shape, just like in sonification, where there's lots of different ways you can map, data onto acoustic or electronic synthesis parameters, and many of which are quite arbitrarily decided, let's say. All right. So having sort of worked out the CAD model for that, I then eventually 3D printed it, and here's the final result that I'm going to show you. I call this object Hypertension, and it's got these spokes that vary in thickness, like you could see on the plastic model. And hopefully these spokes, therefore, that variation will also cause a variation in the acoustics of the object due to the intimacy of the connection between acoustic and shape and resonance. So let's just prove that it actually sings. I hope you can hear that. And there's another really interesting effect because, normally singing bowls don't have all these data spines on them. The great thing about 3D printing is that you can actually create objects that are more complex than can be handcrafted. And embedding the data set into this object actually creates an object with its own acoustic footprint, its own. So I imagine, and I've yet to test it, that's for further work, that different data sets will produce singing bowls with different resonances and harmonics and partials and so on. But listen to it when I ring it. I'll just do that one more time for you. Can you hear, well, there's the vibrato in the tail, or the amplitude modulation in the tail. And there's also this sort of hissing sound, which I think is coming from the partials as the interference between them in the attack sound, which is an interesting addition to the sound of a singing bowl. So there you have it. I'm looking forward. It's great fun. I enjoy this object, and it is does give me a sense of reflecting on my health, and I'm looking forward to printing more of them in the future, trying out different mapping schemes, and also testing whether you can actually really hear information in the data set from the data set. I showed the bowl to a friend of mine who'd just been through chemo for breast cancer, and she asked me whether I could make her several bowls from her blood pressure data that came from her chemo treatment that she could give as gifts to family and carers and nurses at the time. And this really drove home the idea that there's an intimacy about health data that goes beyond just graphing it, and that giving a graph of data to somebody wouldn't be much of a present, but giving them an object like a singing bowl could be a much more poetic and intimate way to reflect on that experience. All right, thanks for your time. I hope some of you might be interested to also do some acoustic sonifications in the future. Any questions? I'm on the line in Australia, ready to answer them after this video. All right, see you later.